Hello and welcome back to my DP chemistry curriculum. We're on lesson 23, reactivity 2.1.1. You'll notice we kind of jump around. I'm following my own plan for how to go through the DP chemistry curriculum. And after ideal gases, I move on to chemical reactions. So uh, we will cover every single topic throughout the series. But for now, we're skipping structure 2, structure 3, reactivity 1, and moving straight to reactivity 2, because I believe chemical equations are how we will deal with everything else we come across. So, chemical equations show the ratio of reactants and products in a reaction. That is incredibly important. By the end of this, we'll be able to deduce chemical equations when reactants and products are specified, and we will be able to include state symbols in our chemical equations, which we already learned about back in, I think, structure 1.2.1 or something like that. Anyways, so why do we have chemical equations? Well, when we look at other things like maybe a recipe for pancakes. Now, this is going to be a terrible recipe for pancakes, but if we have 2 cups of flour, 2 eggs, and 1 cup milk, we take those and we add them together and we get a pancake. Maybe we get 2 big pancakes. So we get 2 big pancakes. Now, let's say we're a little lazy and we want to abbreviate these. So we'll say 2C plus 2E plus 1M makes 2P. Now, I want to abbreviate even further because I know math, and when I'm talking about variables like x plus y equals z, I know that x is the same thing as 1x, and I'm a scientist, so I'm lazy. So I'm going to abbreviate further and say 2c plus 2e plus m makes 2p. You'll notice the only difference here is I got rid of the 1 because we don't need to put a 1 in front of something if there's only one of it anyways. So this is a chemical equation. The only difference is with chemical equations are the same, but our ingredients are elements and compounds. So they don't have to be a single element, they can be a compound. So a molecule or ionic compound. Furthermore, we have some things that we call reactants, and reactants are always on the left of the arrow. These are what react. It's kind of self-explanatory. We also have products. Products are on the right of the arrow. And much like the name says, they are what is produced. So let's look at a real chemical equation. So let's, for example, say we have some potassium, which is K. We drop it in some water, H2O, and those react to make potassium hydroxide and hydrogen gas. Now, I know that I'm going to put some numbers in front of here, and we'll talk about where those come from, but this is a real chemical reaction. We can see that on the left, we have reactants. On the right, we have products. And this arrow kind of just means the words react to form. It can be decompose or synthesize or combust, but the idea is the arrow is the reaction. So this reaction specifically states that 2 potassium plus 2 water react to form 2 potassium hydroxide and 1 hydrogen gas, which you'll notice hydrogen gas has a 2, like H2O has a 2. This is what's called a subscript. These are subscripts and they cannot change. Now, we're going to talk about that big number in front. So each reactant and product has a number in front reflecting the amount of that substance. So this is called a coefficient. The term for that is a coefficient. And like I said before, no coefficient means 1, such as our H2 is the same as 1H2. We have coefficients help us follow the law of conservation of mass. So this is super, super important. We need to follow conservation of mass. We cannot create mass or destroy mass. So if we take our previous equation right up here, and I'm going to rewrite it, but instead of doing coefficients, I'm just going to write things below it. I'll show you what I mean. K and K add to specifically 2H2O, H2O, H2O, and they react to form KOH, KOH, and H2. When we write it like this, it's the same thing as having the 2, 2, 2, and 1 coefficients. But what we can see is that on the left side of the equation, if I put a big divider, we have 2 Ks, 4 H's, and 2 O's. On the product side, we still have 2 Ks, 1, 1, 2, 3, and that 2 means 4, 4 H's, and 2 O's. So you'll notice that it's what we call balance. It is completely even. Without the coefficients, if we do it without the coefficients, K plus H2O reacts to form KOH plus H2, we notice 1 K, 2 H's, 1 O, 1 K, 1 O, and 3 H's are all inverse that so that it reflects the same thing. 3 H's and 1 O. And these are not equal. This means somehow from here to here, we got 1 extra H, which doesn't make sense. We cannot create matter. Therefore, we come back here. We are, oh, one in my highlighter. We are balancing. So we balance the equation. This is what's called balancing. Using coefficients is called, or the application of coefficients is called balancing. This is called balancing. Being very repetitive, but you need to be able to do it. So let's try balancing an equation. So let's do an example. Now this is going to be a very tough example, but what I'm going to do is I'm going to try and figure out how to link other videos as I have one specifically on balancing, and I'll try and do that within the description. So in this example, we have NH3, which is ammonia, plus O2, which is oxygen, and it's going to create nitrogen plus water. And here's how I balance. What I do is I make a big column right in the arrow, dividing the reactants and the products, and I write each element, N, H, and O. And I'm going to count on each side. On the reactant side, I have 1 N. On the product side, I have 2. On the reactant side, I have 3H. On the product side, I have 2. On the reactant side, I have 2 oxygen. On the product side, I have 1. So what I'm going to do is I'm just going to start at the top and see how I can balance it. Now, something you'll notice about coefficients is they go in front. So 2K doesn't mean K plus K, it means 2 times K. So for example, 2H2 means 4 hydrogen. Coefficients are multiplicative. So coefficients multiply. So I'm going to put that up here. Coefficients multiply. So what I'm going to try and do is find a number that I can multiply either the reactant side or the product side to create the other number. Sounds a little confusing, but you'll see when I do it. 1 times 2 makes 2. So 2 is equal to 2. So what I notice is I multiply 2 times the nitrogen on the reactant side. So I'm going to find nitrogen on the reactant side, and I'm going to put a 2 coefficient. Now that affects nitrogen, which did that right there, it's 2, but it also affects hydrogen. So 2 times 3 hydrogen is going to turn this 3 into a 6. So now, as my equation stands, 2NH3 plus oxygen creates N2 plus H2O. So what I'm going to do is the same thing now on this line. I notice that 2 times 3 equals 6. So I'm going to take this 3 and multiply it by our H2O. 3 applies there and we get our 6, but 3 also applies here, turning this 1 into a 3. All right. So nitrogen, still good. Hydrogen, still good now. Now I have to move on to oxygen. This one's a little tough. Now, 2 can multiply by something larger, 3 can possibly multiply by something smaller, but I notice that oxygen's all alone here, so if I multiply it by something, it'll only affect the oxygen, while oxygen already has a coefficient on the reactant side, and I don't really want to change that. So what I'm going to do is I'm going to multiply this 2 by 1.5, which will equal 3. So I'm going to have a coefficient of 1.5. This is now technically a balanced chemical equation. 2NH3 plus 1.5 O2 reacts to form N2 plus 3H2O. The only thing is coefficients tend to be whole numbers. So we have to do one final step just to finish this off. I want to find a way to clear this 1.5 coefficient. Well, the easiest way to change 1.5 into a whole number is multiplying it by 2. But if I do that to that, I must do it to the whole thing. So I'm going to multiply the whole thing by 2, getting me a final equation of 4NH3 plus 3O2 reacts to form 2N2 plus 6H2O. This is a fully balanced equation, but I do want to let you know that this is also considered balanced. The IB tends not to use whole numbers, or sorry, tends to only use whole numbers, but sometimes they will use fractions or decimals as coefficients to throw students off. But know that while this is the preferred way, this is not illegal. This is technically fine. So with that said, let's move to a couple key factors. So in addition, let's go back to the white marker. In addition, state symbols are often necessary. So we learned about these earlier. Those state symbols are S, L, that's a cursive L, G, and AQ. Solid, liquid, gas, and aqueous. Aqueous. This is dissolved in water usually. So a couple ways to easily remember how these state symbols are used is one, an equation will often tell you. So in this previous one, someone might say ammonia gas with oxygen gas reacts to form nitrogen gas and water. Not water vapor, just water. So you know that it is gas, 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 liquid. So usually it tells you, but you do sometimes just have to know for the DP. So I'll give you the general lowdown on how these go. Metals. So any metal is going to be solid with one exception, except Hg. Hg will be liquid. Hg is mercury. Mercury is a liquid at room temperature. Gallium is technically solid, even though it's very close to a liquid. It's liquid just above room temperature. Nonmetals. Nonmetals are almost always gases. Now, there are quite a few exceptions, so we're going to write these out. The exceptions are carbon, which is a solid. You can think about diamond or coal or graphite. Those are all carbon, and that's always solid. Sulfur, S8, usually is a solid. Bromine is a liquid, Br2. It appears as a diatom. Iodine, I2, also appears as a, oops, not liquid. It appears as a solid. And phosphorus, P4, also appears as a solid. So, with the exception of these 1, 2, 3, 4, 5 elements, nonmetals are almost always gases. So, lastly, we have ionic compounds, or second to last, ionic compounds, like salt. These are pretty much always solid, unless dissolved. If dissolved, if dissolved, then it's aqueous because that's what aqueous means, dissolved. And then finally, we have molecular compounds. So, like, molecules are just dependent on situation. So those will often be told to you, such as things like hydrazine or sucrose or hexane. They'll tell you, the DP will tell you what you have to do with those. So let's do one quick example of using state symbols. Our first equation, 2K plus H2O, reacts to form KOH plus H2. As we analyze this, oh, I should finish putting these here. As we analyze this, K, that's potassium, that's a metal. Metals are solid. H2O, that's water, and usually water is going to be in its liquid phase. KOH, that's a metal and a polyatomic nonmetal. This is what we call an ionic compound. We'll learn about them later, how to make sure you know which is which. If it's an ionic compound, and check it out, we had water, which means there's still probably water. This is going to be aqueous. So that informs that. And lastly, H2, that's a nonmetal. Nonmetals are gas because it's not one of the 5 listed here. Therefore, we have all 4 state symbols in this simple equation. So hopefully this helps, and have a great day.